Oh, so this was right. Oh, but it's just like 8. Okay, 29 is done. 37, 57, 60. I think 37 was the one that was kind of hard, actually. Okay, all right. Let me actually figure this one out now. So we have this big plate. This thing is due at midnight. I don't know why I'm like trying to throw my life away. Okay, so this ray comes in, and it reflects straight back up. Now this one, This one's hard. At least for me conceptually, this one's challenging. Thin film interference. Because let me just read it again. Because there's a flip, but then there's a which is a pi. Okay, yeah. So this is when no this so when 2t is equal to lambda n over 2 constructive. If the extra 2t traveled by ray 2 corresponds to a multiple of lambda n, the two waves combine out of phase and the result is destructive interference. The general equation for destructive interference in thin films is 2 times the index of refraction times the thickness of the gap equal to some integer multiple of the wavelength. The one thing that I don't understand is that okay, got it. All right, cool. That one makes sense now. All right, now 57. Okay, wait, this one's fun. They need more hotkeys. That's the biggest grip I have. Oh, okay. All right, so then 3/2 lambda becomes lambda is equal to dy over L. So then okay, wait. So this is 37.57. Okay, so let's just get all of our parameters down. So lam equals 500 nanometers. L equals 100 meter. H equals 1 centimeter. So D equals 2H. So then um um oh yeah, and Y equals the unknown. Yeah, it doesn't wasn't smart enough to inspect the contents of ants. Why didn't that work? That's so weird. Wait, you can't. Oh wait. Oh, I see. It's like nested so weird. I should just be able to do... Right? Oh, wait, SI. That seems good. Oh, I can just do this. Oh, but you know what I didn't do? I didn't, 1 over 400... 2.5 millimeters. Ba-boom, baby! That's easy. That was actually easy. Alright, so last problem for this chapter. We can read the next chapter. 60. Bruh, I can't believe this exam is due tomorrow. And chem. I hate finals. So stressful. Alright. Oh, this one's fun though. I like these double slit problems. They're actually not that hard. Okay, D L P R1 R2 theta D or delta O. And now here the extra part is this thing. N comma T. Okay, so the question is, if we have this light through this thing, so N is equal to C over V. So V is equal to C over N. So what we want to know, consider the double slit arrangement shown in the figure. Where the slit separation is D and the distance from the slit to the screen is L, a sheet of transparent plastic having an index of refraction N and thickness T is placed over the upper slit. As a result, the central maximum of the interference pattern moves upward a distance y prime. Okay, so C is in units of meters per second, right? So if we want to travel a distance T, or we want to travel a distance, T, that's so confusing. I'm going to call it D. Whatever, T. I'll just have to remember that's not time. Or I'll call it W. This is W. If we want to travel a W, so the width over the speed of light is equal to the time in no sheet. And then W over V is equal to T with sheet. And this is equal to W C N W N over C. So then the difference in time So we can find the difference in time, but then we need to convert that to a path difference. So the difference in time is going to be equal to W over C minus WN over C. Wait. No, yeah, T sheet takes more time. This is the absolute value. So W over C times N minus 1. This is a time measurement. Now, delta normally is equal to D sine theta, where sine theta is approximately tan theta, which is equal to y over L, or y over L. So then delta is equal to dy over L. And delta is a maximum, delta constructive, when delta is equal to m lambda, because that's just what it is. And so if we did m lambda is equal to dy over L, and we did the central maximum is equal to m over equal to 0, so then dy over L is equal to 0, so y is equal to 0. But now the problem is that we're going to have a shift factor. This gets shifted because the path length will be dy over L minus the, or actually, wait, will it be minus or plus? It should be minus. Whatever the distance is, I think that we just multiply delta t times c is equal to the change in delta. So then we're going to get w, or we'll convert this back, or w to n minus 1. So I think this should be t n minus 1 is equal to 0. Oops. Uh, Ugh. All right, nice. All right. So now the next chapter in my learning. The fraction. I think this one is long. Oh no, it's not. Well, I don't know. I don't know how many pages it is, but take a walk around the block, come back, and crush it. When plane light waves alright, so here we go. Diffraction patterns and polarization. When plane light waves pass through a small aperture in an opaque barrier, the aperture acts as if it were a point source of light, with waves entering the shadow region behind the barrier. This phenomenon, known as diffraction, was first mentioned in chapter 35 and can only be described with a wave model of light. In this chapter, we investigate the features of the diffraction pattern that occurs when the light from the aperture is allowed to fall upon a screen. We learned that electromagnetic waves are transverse. That is, electric and magnetic field vectors are associated with the electromagnetic waves are perpendicular to the direction of wave propagation. In this chapter, we show that under certain conditions, these transverse waves with electric field vectors in all possible transverse directions can be polarized in various ways. In other words, only certain directions of the electric field vectors are present in the polarized wave. Introduction to diffraction patterns. We discussed that light of wavelength comparable to or larger than the slit spreads out in all forward directions upon passing through the slit. This phenomenon is called diffraction. When light passes through a narrow slit, it spreads beyond the narrow path defined by the slit into regions that would be in shadow if light traveled in straight lines. In other words, such as sound waves and water waves, other waves such as sound waves and water waves also have this property of spreading when passing through apertures or by sharp edges. That's weird. You might expect the light passing through a small opening would simply result in a broad region of light on a screen due to the spreading of light as it passes through the opening. We find something more interesting, however. A diffraction pattern consisting of light and dark areas is observed. Test. Somewhat similar to the interference patterns discussed earlier. For example, when a narrow slit is placed between a distant light source or a laser beam and a screen, the light produces a diffraction pattern like that shown here. The pattern consists of a broad, intense central band called the central maximum, flanked by a series of narrower, less intense additional bands called side maxima or secondary maxima, and a series of intervening dark bands or minima. Figure 38.2 shows a diffraction pattern associated with light passing by the edge of an object. Again, we see bright and dark fringes, which is reminiscent of an interference pattern. Figure 38.3 shows a diffraction pattern associated with the shadow of a penny. A bright spot occurs at the center. Whoa, that's freaky. I didn't even notice that. And circular fringes extend outward from the shadow's edge. We can explain the central bright spot by using the wave theory of light, which predicts constructive interference at this point. From the viewpoint of ray optics, in which light is viewed as rays traveling in straight lines, we expect the center of the shadow to be dark because that part of the viewing screen is completely shielded by the penny. Shortly before the central bright spot was first observed, one of the supporters of ray optics, Simeon Poisson, argued that if Augustin Fresnel's wave theory of light were valid, a central bright spot should be observed in the shadow of a circular object illuminated by a point source of light. Diffraction patterns from narrow slits. Let's consider a common situation, that of light passing through a narrow opening modeled as a slit projected onto a screen. To simplify our analysis, we assume that the observing screen is far from the slit, and the rays reaching the screen are approximately parallel. This situation can also be achieved experimentally by using a converging lens to focus the parallel rays on a nearby screen. In this model, the pattern on the screen is called the Fraunhofer diffraction pattern. The figure shows light entering a single slit from the left and diffracting as it propagates towards the screen. Shows the fringe structure. Okay, B shows the fringe structure of a Fraunhofer diffraction pattern. A bright fringe is observed along the axis at theta equal to 0, with alternating dark and bright fringes on each side of the central bright fringe. Until now, we have assumed slits are point sources of light. In this section, we abandon that assumption and see how the finite width of slits is the basis for understanding the diffraction pattern. We can explain some important features of this phenomenon by examining waves coming from various portions of the slit as shown in Figure 5. According to Huygens' principle, each portion of the slit acts as a source of light waves. Hence, light from one portion of the slit can interfere with light from another portion, and the resultant light intensity on a viewing screen depends on the direction theta. Based on this analysis, we recognize that a diffraction pattern is actually an interference pattern in which the different sources of light are different portions of the single slit. Therefore, the diffraction patterns we discussed in this chapter are applications of the wave and interference analysis model. Diffraction versus diffraction pattern. Oh, okay, I think I already fell through that for this. Diffraction refers to the general behavior of waves spreading out as they pass through a slit. We use diffraction in explaining the existence of an interference pattern. A diffraction pattern is actually a misnomer, but is deeply entrenched in the language of physics. The diffraction pattern seen on a screen when a single slit is illuminated is actually another interference pattern. The interference is between parts of the incident light illuminating different regions of the slit. To analyze the diffraction pattern, let's divide the slit into two halves. Keeping in mind that all of the waves are in phase as they leave the slit, consider rays 1 and 3. As these two rays travel toward a viewing screen far to the right of the figure, ray 1 travels farther than ray 3 by an equal amount to the path difference, A over 2 sine theta, where A is the width of the slit. Similarly, the path difference between 2 and 4 is also the same with 3 and 5. If this path difference is exactly half a wavelength, corresponding to a phase difference of 180 degrees, the pairs of waves cancel. A destructive interference results. This cancellation occurs for any two rays that originate at points separated by half the slit width. Because the phase difference between two such points is 180. The general condition for destructive interference is that sine theta dark is equal to m times the wavelength over A, which is the slit width, for m greater than 0. Or no, for m not equal to 0. This equation gives the values of theta dark for which the diffraction pattern has 0 light intensity, that is, where a dark fringe is formed. It tells us nothing, however, about the variation in light intensity across the screen. The general features of the intensity distribution are shown in a figure. A broad central bright fringe is observed. This fringe is flanked by much weaker bright fringes alternating with dark fringes. Each bright fringe peak lies approximately halfway between its bordering dark fringe minima. Note that the central bright maximum is twice as wide as the secondary maximum. Suppose the slit width is made half as wide. Yes, it becomes wider. I think, because the reason it becomes wider is that this number is going to get bigger. And sine is at a maximum at plus minus pi over 2. So theta has to grow. When more than one slit is present, we must consider not only diffraction patterns due to the individual slits, but also the interference patterns due to the waves coming from different slits. Notice the curved dashed lines in that figure. I remember them, which indicate a decrease in intensity of the interference maximum as theta increases. This is due to a diffraction pattern. The interference patterns that figure in that figure are located entirely within the central bright fringe of the diffraction pattern. So the only hint of the diffraction pattern we see is the fall off in intensity toward the outside of the pattern. To determine the effects of both two-slit interference and single-slit diffraction pattern, we have to multiply the intensities. Okay. The blue curve represents the factor in square brackets. The cosine squared factor by itself would give a series of peaks all with the same height as the highest peak in the red-brown curve in figure 38.7. Because of the effect of the square bracket factor, however, these peaks vary in height, as shown, and diminish, really. Equation 37.2 indicates the conditions for interference maxima as d sine theta is equal to m lambda, where d is the distance between the two slits. Equation 38.1 specifies that the first diffraction maximum occurs when a sine theta is equal to lambda, where a is the slit width. Equation 38.1 specifies that the first diffraction minimum occurs when a sine theta is equal to lambda, where a is the slit width. Dividing equation 37.2 by equation 38.1 with m equal to 1 allows us to determine which interference maximum coincides with the first diffraction minimum. Hmm. The ability of optical systems to distinguish between closely spaced objects is limited because of the wave nature of light. To understand this limitation, consider figure 38.8. Okay, the figure shows two light sources far from a narrow slit of width A. The sources can be two non-coherent point sources S1 and S2. For example, they could be two distant stars. If no interference occurred between light passing through the different parts of the slit, two distinct bright spots or objects, two bright distinct spots or images would be observed on the viewing screen. Because of such interference, however, each source is imaged as a bright central region flanked by weaker bright and dark fringes. A diffraction pattern. What is observed on the screen is the sum of the two diffraction patterns, one from S1 and the other from S2. As the two sources are far enough apart to keep their central maxima from overlapping in part A, their images can be distinguished and are said to be resolved. If the sources are close together, however, the two central maxima overlap and the images are not resolved. To determine whether two images are resolved, the following condition is often used. When the central maxima of one image falls on the first minimum of another image, the images are said to be just resolved. This limiting condition is known as Rayleigh's criterion. From Rayleigh's criterion, let's read it one more time. When the central maximum of one image falls on the first minimum of another image, the images are said to be just resolved. This limiting condition of resolution is known as Rayleigh's criterion. From Rayleigh's criterion, we can determine the minimum angular separation theta min subtended by the sources at the slit. For which the images are just resolved. Equation 38.1 indicates that the first minimum in a single slit diffraction pattern occurs for which sine theta is equal to lambda over the slit width, the wavelength over the slit width. Hence, the angle subtended by the two sources at the slit must be greater than lambda over A if the images are to be resolved. Many optical systems use circular apertures rather than slits. The diffraction pattern of a circular aperture Oh yeah, that's true. That's a pretty good image, though. I'm not getting this part, dude. Honestly, this stuff is like, how does slit width, like slit width doesn't have anything to do with it, but it does. But I don't see how slit width has any impact here in this photo. But it says that the minimum angle is dependent. So if I decrease, if I increase the slit width, the diffraction grating, a useful device for analyzing light sources, consists of a large number of equally spaced parallel slits. The transmission grating can be made by cutting parallel grooves on a glass plate with a precision ruling machine. The spaces between the grooves are transparent to the light and hence act as separate slits. What the fuck are they talking about? Oh shoot, I think I need to go inside for a bit.